All right, we're starting the next section today for our unit. So you can see here, title is 1.3. We're going to be finding limits analytically, right? Analytically is just another word for algebraically. So you can assume that that is what that means. Okay. So much like the Spinjitzu masters, right, have 4 weapons of Spinjitzu, the calculus student has 4 ways to handle the problems that you encounter. So these are the 4. First way, right, is algebraic manipulation, right, being able to know your notation, write things accurately. Okay, the second thing is to be able to do a graphical representation, which we started with yesterday in looking at limits. Okay, that goes for any other problems that we do. Can you create a graph of it, or can you analyze the graph of something? And can you predict other graphs from what you see? The third way of the AP Calc student is numerical analysis. So can you look at data? Can you look at a table? Can you look at information about numbers and draw conclusions about what they mean in terms of calculus? And last but not least, let's go yellow. There is your written explanation, right? Can you write a logical sounding sentence using standard calculus vocabulary to communicate what you're thinking, right? Right in here, in the middle of all of this Venn diagram, right? This is where the 4 and 5 AP student lives. They are effortlessly able to do, right, all 4 of these simultaneously. Others of us can get caught up in other pieces of this Venn diagram, or good at some parts and not others. But that's what it takes to really do well in this class, is that you can't be just, good at algebra. You have to really be a thinker and a writer and a doer and a knower of everything. Okay, pertaining to calc. So let's get on the way. This is where we are today. We're going to work on some algebraic manipulation of limits. So we've got 3 examples here. You'll notice they all have the exact same function. If you'll notice, all 3 limits are just different values on the function. So the first one is having us take a look at the limit as x approaches 2 of this function. So like we said the other day, if you have an explicit function like this, what you can do is you can just go ahead and you can plug 2 in, right, for all the x spots, just like this. Right, and then try to work that out notationally, right? I'm working top to bottom. I'm using equal signs to show, right, all that equality. And then I'm simplifying and showing my in-between steps. I can go over here is fine, and get 8 minus 15, and 4 minus 6, right, is negative 2. And then negative 7 up here, negative 2 here. And then that's enough to say that limit at that x value of 2, this function must have a y value of 7/2, right? Which makes sense, because we basically took the x and plugged it into the function. So in this case, the function's y value and its limit are exactly the same. Okay, let's see what happens in these other cases. Let's take this limit here. I'm going to plug in 0. Okay, just like the previous example. And I'm going to do a little analysis here and see what these numbers show me. So I've got basically negative 15 on top is all that's left. And then I'm dividing by 0 here on the bottom. Okay, now this expression in and of itself does not exist, right? What we should do is just make sure we know for sure that that's not not a whole, see if it's an asymptote, and do some analysis about the graph of this function to make sure that the limit also does not exist, right? So if I plug in 0, or not plug in 0, but if I want to analyze a rational function, right, the best thing for me to do is to factor it. So I'm going to factor the numerator. Should be that. I'm going to take the GCF out is all I can do of the denominator, right? It does look like I have a whole, but clearly the whole is not at the given, right, x value of 0. The whole should be at x equals 3. So what is 0, right? Well, 0 is the location of this uncanceled factor in the denominator, right? And we know that historically, wherever this does not cancel out, at wherever that factor equals 0, I actually have a vertical asymptote. Okay, now at a vertical asymptote, right, whether, different ways that the graph could go, it could go up, right, towards, the very top end of the graph, but we call that behavior unbounded, right? It could switch, right? So in that case, right, our left and right hand limits at 0 are going to the same place, but it's heading off towards infinity, and then we're not going to say that a limit exists if it's heading towards infinity. Right, we can also, have rational functions doing this, right, heading off in different directions, so definitely that limit doesn't exist. And then lastly, of course, is if it was both headed down, that's just basically the opposite of if, both were headed upwards, so it's also unbounded. So when we have asymptotes like that, it is super cool to say does not exist. Okay. The last example then is plugging in, finding the limit at 3. So we're going to try to plug that in first. See what we get when we do this. Let's see, 9 plus 6 minus 15, all over 9 minus 9. Oh boy. I get 0 over 0. Okay, now this is a very interesting expression. This is worse than does not exist. It is what we call indeterminate. So this is a very fancy word to describe this expression. Indeterminate. I want you to say it out loud wherever you are right now. Indeterminate. Sounds super smart. Okay. This means, we kind of have a rule that says 0 divided by anything is 0, and we also have a rule that says anything divided by 0 doesn't exist, right? Well, if they're both zeros, 0 divided by itself, should that equal 1? Should it be 0? Should it not exist? See, this tug and push and pull of all this rules that we've set up for ourselves doesn't really work. So what we're going to have to do, if the numerical plugging in doesn't work, we're going to have to, try to look at this analytically. So if you remember back in the previous box, right, when we factored this out, we knew that whole was at the x value of 3, right, because that's the term that canceled, and that happens at 3. So we know there's a hole there. Well, if I can cancel that out, what I can do to calculate this is to take the limit of what remains. So I'm going to take the limit as x approaches 3 still, but now I'm just going to reduce it to x plus 5 over x, right, in an attempt to plugging in 3 gives me the y value of that whole, right? So it must be 8/3. And that's our workaround for the whole, is to go ahead and factor and cancel. Remember, the difference in example 2 was that we were finding the limit at a totally different value. So that canceling didn't really help us over in example 2. Okay, so these are our steps for finding limits algebraically. We're always going to try direct substitution first, and always. If that doesn't work out, next best thing to do is to factor, to cancel, resubstitute after you do all that, and see if you can then get it to work. That's what we did right here in example 3. And then lastly, if we can't figure out anything from this line of work, we're going to move on to a graph or a table of the function. And then again, we're going to cover tables tomorrow. All right, last couple examples here. We've got limit as x approaches pi of sine of pi over 2. So we're going to try direct substitution. And we're going to try to remember what the unit circle says sine of pi halves is. Okay, I urge you to look at a picture of the unit circle and not type this into your calculator to get that answer of 1. Okay, it's really going to be beneficial to you to rememorize the unit circle if you have forgotten it. Okay, here in calc, we mainly work, I would say, between, I would say 0 and 270 degrees, right, or 0 to 3 pi halves. We usually don't go all the way to 2 pi, but occasionally it pops up. But if you at least know even the top half of the unit circle, you'll know a lot more than some other people. So that would be great. Next one, we're switching it up to secant and a different limiting value, right? X is approaching pi halves. So I'm going to plug in pi halves like this, okay, and reduce that to secant of pi fourths, which you probably don't know. If you do, pat yourself on the back. That's super great. But what you might have a better chance of remembering is that secant is the reciprocal of what function, right? What is secant the reciprocal of? And that is how you want to calculate this, right? It is the reciprocal of cosine. So 1 over cosine of pi fourths is 1 over root 2 over 2. Now, as we prepare for the AP test way next year, right, we want to think about how this will look on a multiple choice test. This would an answer would never appear like this. So if you had to pick this out of A, B, C, D choices, it's not going to have a complex fraction in it. What we are going to have to do is actually multiply instead by the reciprocal of that denominator, right? And the way that this answer would look is 2 over root 2. There is no rationalizing, right, in calculus, okay? So we don't make use of rationalizing. So 2 over root 2 is how your answer would look. You don't ever have to simplify, you don't ever have to rationalize that, okay? Last little bit here is properties of limits. It looks fancy, but it's really just basic arithmetic they're trying to tell you here. That if you have a limit for, let's say, a function f, and its limit is L, okay, and you have a function g, and its limit is k, those are just stand-ins for what numbers they equal. Basic arithmetic applies. Like for number 1, you can just multiply, right, if you're multiplying by a scalar, just a little number b, times f of x, you can do that first to the function and then take the limit, or you could find the limit of f of x, which we know is L, and just multiply it times b. So there's just like 2 ways to go about it. Same works for sum or difference and a product. We say that sum or difference, we can take the limit of the sum, or we can also do the sum of the limits. That's what both sides of this equal sign show. Okay, so you can kind of do it in any order. Limits first and then add them together, or add the functions together and then take the limit. That's all it means. Same is true for products, quotients, and powers. Okay, so if we look down here at this one last example, hang on, we're almost there. This is the given information for this problem. The limit for function f is 3/2, and for g, it's 1/2. So if we're going to do part A here, we're going to apply, right? We have 4 times the function is what I'm looking at here. And that's just the scalar multiple rule. So I can just take and multiply 4, right? This is property number 1. So I can just go ahead and take that scalar, like b up here, and multiply it times the limits value, which in this problem is f, which is 3/2. Okay, remember that this is like 4 over 1 times 3 over 2. 12 divided by 2 gives us a big fat 6. Okay, part B. If we are going to take the sum of the limit of the sum, we can just do the sum of these 2 limits, right? So we're going to this would be property number 2 in this box, and we can just do 3/2 plus 1/2 to give us 4/2, which is 2. And then part C is the same thing for a product, so that just means multiply, right? This is property number 3, 3/2 times 1/2, straight across to give us 3/4. And then last but not least, purple, question D is the quotient. So as long as that g function doesn't have a limit of 0, we can go ahead and apply property number 4 and do f limit divided by g limit. Remembering what we just said earlier about multiplying by the reciprocal, right? This gives us 6/2, which is 3. And that's it.